Yeah, I'll share my screen. Okay, so today we will be going over this weird title, The Unreasonable Ineffectiveness of Deeper Layers, and it is actually quite an interesting paper. Um, it goes on to show that how many layers are sort of redundant when it comes to specific task, and how we can remove multiple layers from our architecture, um, and reduce the inference cost or the memory required to run our models. So the uh, I mean, in our reading group, we have been, always trying to understand what exactly happens inside transformers. So I remember a year back we were reading on something about knowledge neurons and trying to understand where exactly is the information stored about something in transformers, and what sort of interactions have to take place for for us to get some generational output from the models. So this paper is interesting because of not only we can remove so many layers and still get good performance from these models, but it also gives us an idea of what exactly is happening inside the transformer architecture. Um, so the authors here, they find minimal degradation of performance on different question answering benchmark until after a large fraction, up to half of the layers are removed. So they remove, let's say if they had 20 layers in their pre-trained model, they remove 10 layers, and just with small fine tuning using QLoRa, they have minimal degradation in performance. And they also highlight that the robustness of these LLMs to deletion of layers implies either that the current pre-training methods are not properly leveraging the parameters in the deeper layers, or that the shallow layers play critical role in storing knowledge. So there has been a lot of papers already which are trying to understand what is the optimal number of optimum amount of data that we should pass to the model for best training, or what should be the number of parameters. So if what this paper shows is you can remove so many layers, then we really don't understand how many parameters are actually needed. And they show that the deeper layers, so here in this paper, the shallow layers are the ones which are closer to the input, and the deeper layers are the ones that are closer to the output. So the authors here say that the deeper layers of the network might not be that important for um, for the performance of transformer models. So the methodology in this paper is that they develop a method to find similarity between representation at different layers to identify the optimal layers to prune. A very naive approach would be, we just, let's say we have 20 layers and we just remove the first five of them, or the last five. But the idea here is to find layers which are very close to each other in representation, and remove those layers based on certain criteria. And once they remove those layers after following a particular criteria, they have to heal the pruning induced mismatch with a small amount of fine tuning using QLoRa. So uh, the authors here, like for Llama 270B, they can eliminate up to roughly half of the layers before they even see any performance collapse. And yeah, the result section of this paper is really interesting. We will go through it in thorough details. And their assumption basically in this entire paper is that the output of the final layer can be decomposed as a sum over the outputs of all model layers plus the embedded input. Obviously, we know that they are not independent of each other, but they're trying to test these waters, assuming like, can we think of the entire transformer architecture as a parallel computer, which is something I heard from Andre Karpathy. He said like you can think of transformer architecture as a parallel computer where basically all the skip connections that we have, we think of the entire architecture as something that is stacked on top of each other. but we can think of it, instead of being stacked on top of each other, we can think of everything as is it is in parallel to each other because of the skip connections. So their assumption is that all these parallel, components in this architecture, if they can they treat them as independent, and if they can treat them independent, how many of these components can they remove? Yeah. So basically, they want to remove the components whose contribution to the overall output is very small. So this basically changes how we use LLMs for specific tasks. So some time back, we were introduced to the PEFT parameter efficient fine tuning methods like LoRa, and now people are not fine tuning anything without LoRa or QLoRa or the quantized version of LoRa. So being able to train on lesser number of parameters is a huge advantage, and I think this paper is kind of something more in the next direction of, like, if we want to fine tune, or let's say if we have a llama 2 model and we want to fine tune on a particular task, first we might as well check how many of those layers in that model are redundant, and then go ahead and fine tune, which drastically reduces the memory footprint that this our fine tuning would need. So yeah, so this method definitely decreases the memory footprint and the inference time, and they were able to do all these experiment on a single A100 GPU, which is basically what most of the researchers have access to, and it highlights the robustness of the model of removing the deeper layers. So it's like if you have a train of 20, not 20, like 3 engines, and you can just do the same thing with 2 engines, why would you use those 3 engines? So yeah, and surprisingly the models still do well after removing those last layers. So okay, so yeah, talking about literature survey, now pruning has been an idea which people have experimented with a lot. So initial experiments were around, were about dropping attention heads, or like, let's say if we have 8 attention heads, what happens if we remove 2 of them, and to directly dropping a number of layers, or removing the hidden states to so most of the contribution, most of the research in this domain has been about removing single aspects, and I don't there has not been there has been studies on bird style models where they are talking about entirely dropping layers, and as per the authors, there has not been much work in this direction for GPT style models, which are basically decoder only, and yeah, so here they are removing the entire layers, and which is not been worked on so much. Model distillation is another concept where you basically try to get a smaller version of the model by distilling the knowledge from a teacher to a student model, and yeah, that is another, you can say, another method of thinking, that we can remove extra weights from the model and get the same performance from a much smaller student model. So that is like another parallel stream. And other methods include about efficient fine tuning and inference acceleration, basically PFT and LoRa methods, which we have um, discussed in our previous meetings. And there have been a lot of depth dependent studies, and these are basically around trying to understand what exactly happens in the transformer layers. So this 68 and 69 both are the papers that we have covered earlier. One of them is about knowledge neurons, and the other one was about GPT factual association. So in both of these papers, when we discussed them, one interesting thing that we were so again, both of these papers were designed for factual data, So let's say in New Delhi is the capital of India. Now, what they did was they tried to change the input from New Delhi is the capital of, let's say, USA. So, which neurons did fire differently? So, that kind of tells you where exactly is the information stored in the model. And and basically, in those papers, the author said that suggested that the knowledge is the factual knowledge that the model has is mostly stored in the middle layers, and the reasoning is happening in the in the deeper layers. And so those were very interesting papers that we covered in our earlier meetings. And so this particular paper investigates the way facts are processed during inference, and it tries to distinguish between the role of attention heads for attribute extraction and MLP blocks for subject enrichment. So yeah, attention heads were relevant for getting the right attribute, and MLP blocks for uh, enriching the information about the subject. And another interesting thing was that we covered in earlier meetings also, that uh, the information that is stored inside transformers is spread across many layers and spread across many neurons. So it is not like, let's say, in layer number 20, neuron number 10 will have all the information about India. So it is like something like, it's like a collective processing between components in different layers, and through some sort of a complex process that we still don't understand, like how does it come to that particular result. But the information is stored over across the architecture, not in a very distant way, like it won't be like the same information will be stored in layer 1 or in layer 20. But let's say if you're talking about knowledge, so the information about India would be somewhere in the middle layers. So yeah. So before I go over method, any questions till now? Okay, I'll go ahead then. So the mathematical notation here is straightforward. Basically, the input to the layer L plus 1 is basically the input to the layer L because of the skip connection, and whatever happens to the inputs when we pass it through the parameters of that particular layer L. So f of this, basically this function is denoting whatever output that we get after passing it through a self attention head and an MLP layer. So X of L is basically the output that we get, and we can think of the entire thing as the input to the first layer. This X of 0 is the input after getting the embeddings, and a sum, a linear sum of the results of all the layers that are out there, that are there between the input and the output. Again, the assumption here is that they are assuming that all these components, all the function values are independent of each other, which is not so. So the idea here is that, let's say if they remove a particular layer L, so they are reconnecting the input to the removed layer as the input to the uh, yeah, to the layer after uh, layer which was removed, after the layer which was removed. So in this way, they are basically trying to say that, let's say if we have 10 layers and we remove layer number 4 and 5. So basically what will happen is that the output of layer 3 would be the input to layer 6 now. And they're assuming that this would induct some sort of error. And yeah, so the idea is like, what is the number of layers that they can remove such that this error that is induced stays reasonable. And The from this they are trying to they have the following hypothesis that we'll try to test experimentally, which is like we should be able to prune layers of a residual network, and they should be able to have great success in removing deeper layers. So they good. And next we have to cover like what is the metric that they are using to find similar layers. And their algorithm for pruning is very simple. Basically, they pick a number of layers that they want to remove. So it is sort of like a hyperparameter. Like they will decide we have to remove two layers, and then they will calculate the angular distance of each layer between the input to the uh, uh, between the input to the layer L and the input to the layer L plus N on a neural pre-training data set. And they will basically find that particular layer which will remove for which the angular distance between the n layers around that particular layer is the minimum. So basically for layer 3 it will, if we have n equal to 2, it will check for layer 3. It will check for layer number, let's take n equal to 3, then it will check for layer number 3. It will check layer 2, 3 and 4. And basically it will check whether if we remove layer 2, 3 and 4, like if layer 2 and 4 are much more closer to each other than um, let's say layer 7 and 8. And the metric that they used to find angular distance is this. I don't know what this particular function is, but yeah, this is the metric that they used. And once they have decided the which layers they have to remove, they optionally heal the mismatch at layer L plus 1 with a small amount of fine tuning. And they also find that even if they don't fine tune some of the QA benchmarks, it has uh, no degradation in performance whatsoever. And they also tested different pruning strategies, very straightforward ones, like let's say just drop the last 5 layers of the model, excluding the final layer, because they identified like the final layer right before the input. That is really important for any model whichever they tested, because it is doing some sort of a reasoning. And yeah, so one of their naive approaches was just to drop last 5 layers, excluding the last one. So let's talk about results now. So another thing that we have to consider is that they have tested this only on QA benchmarks. So the same kind of performance might not be there on, let's say on translation or some other task. So that is something that we have to keep in mind before discussing the results. So they pruned a wide variety of large-scale LLMs from 2.7 to 70 billion parameters, and they removed up to 32 to 80 total. Uh, oh, no, sorry, parameters spanning 32 to 80 total unpruned layers. They used model from the Llama family, Quen family, and the Mistral family, and the Phi 2. And the fine tuning is done using QLoRa because it allows for very reduced memory requirements, and the fine tuning is done on the C4 corpus. So if we see here the interesting part, the result. So if you here see for this figure, in these three figures, they're talking about the accuracy on different model families: Quen family, Llama family, and Mistral family. And on the y-axis, you have the MMLU accuracy. Now, MMLU is a multi-choice data set. So the random selecting accuracy, it would be around 25%. So On the x-axis, you see the fractions of the layers dropped, and you can see here, like even up till, if you remove 20% of the layers in the llama models, the performance is not degrading. It's only after like we remove zero point 0.3, like almost 30% of the layers, that's when the performance degradation starts. And it something happens after the point of, after removing 40% layers of the model, that it is not able to figure out, like it is something like catastrophic forgetting, like it is not able to, you know not able to perform well on the model. So in llama family models, you can remove up to 30% of the layers. In Quen family, it is around 20%. And in the Mistral family also, you can see that up to 20%, after removing even 20% of the layers, the model accuracy is still nice. So it is quite interesting because, let's say, in especially in llama family, you can remove up to uh, 30% of the layers and you will still get the same performance. Again, the layers that they have removed here is based on finding the ones which have uh, which have the most similar angular distance. And if you see here in the, if you even heal these models, right, then you can continue to get their performance for some time more also. So if you see here, with no healing, this model stops right after 30, removing 30% of the layers. But if you continue to heal it, it is still able to work well till we remove 40% of the layers. So healing sort of offsets the effect of removing these similar layers. So this all implies that the essential knowledge required to achieve a model's top score isn't removed by significant layer removal, even though a fraction could be quite large. Like we just saw that we can remove 30% layers of llama model and still get good performance, until eventually that knowledge is lost at a critical model dependent threshold. So as we saw here, like if we remove 40% of layers of llama, we can't, the model performance degrades a lot. And the same point for Quen family is 20%. So that thing depends on the model family. And the author suggests that broadly they see that layer pruning is more robust for larger and deeper models. So let's say if
Okay,
we,
so one question. So by layer pruning, they're pruning like the entire layer, or they just removing some of the weights?
sorry, what?
You might have mentioned this. I think I missed it. But by layer pruning, are you saying they're removing the entire layer, or they're just removing parts of the weights? It's like sampling from the
No,
layer.
they're removing entire layer. So let's say
Okay.
if they had 10 layers, they will remove layer 4, 5, 6. So the
Okay.
input to the layer 3 would be the output of the layer 3 would be the input to the layer 7 now.
But you
So
can
the,
only remove layers that are like the right dimensions, right? Or else you'll actually change the architecture.
no, all the layers have the same hidden dimension, right? That is why we have skip connections also.
Got
So
it. Got it. Yeah.
yeah, so all of them have the same dimensions. Yeah. So they say that the bigger the model, the more robust they are for removing, their deeper layers. And the either the smaller models are more overtrained, making parameters less redundant. So let's say if we have like only, smaller models, like especially here Quen family, maybe because they have number of the parameters that they have are less, so there is a much more overtraining that is happening over the data so that they remember a lot of information. So if this is true, then uh, basically this shows that the amount of overtraining that might be happening in these bigger models, because let's say if we are able to remove so many layers, and there is an interesting part of the results which we will cover. it shows that we can remove so many layers. So that just shows that these models might be getting overtrained. And basically the efficiency of each and every parameter in the model is not that high. Okay. And this particular uh, uh, so here basically they are showing the validation loss for inference on C4 dataset. Okay. And if you see, this is for, okay, this is for all the figures, or for all the models that they tried. And up until they removed even 20% of their layers in each of these models, the performance still same remains same when they were not healing or like adjusting the parameters through some sort of a healing with QLoRa. So when they did that, if you remove 20% of the layers, let's say if we have 100 layers, if we remove 20 of them, then uh, the model still performs. It is still giving the same validation loss on the C4 dataset. And if we do healing, then the model performance does not degrade that much also. So if we see here, if we remove 50% of the layers, 50% of the layers, and we do some sort of a healing, like some sort of a small fine tune after that, the model is still able to give good results for the C4 validation loss. So it just shows that how quickly the models can switch to good performance even with so many layers after removal.
So healing, sorry, so you said healing is fine tuning it one more time after the thing
Yeah,
has been dropped.
healing is fine tuning. Yeah. They have not mentioned how much, but it won't be like you have to train for one entire epoch for on the entire C4 dataset again. So this is for figure 3, which we okay. So without healing, we see the authors see that there is somewhat sharpish transition to random guessing for each model at approximately the pruning fraction that the QA benchmark accuracy is also sharply transition to. So here you can see that. So here you can see that. So this was for a QA benchmark, okay, and similar kind of patterns are happening when we're trying to check the validation loss for C4 also. So for Llama family, if you can see that the drop starts happening after 30% of layer removal, we can see the same pattern here for the C4 loss. So this kind of shows that this sort of robustness to layer removal is not just it is something much more dependent on the model. It is somehow how the information is stored in that model. That is why it is the same kind of behavior is happening across different models. And and most strikingly, from a scientific perspective, it is the post-healing continuity through the pruning fractions where the authors previously found sharp transition for QA benchmarks. So again, even with this healing, the like even if you remove 50% of the layers, it's the model is still not having such a drastic degradation in performance which we might have expected. It's like literally removing half of the model, but you still get the same performance. And this just shows the robustness of these autoregressive models and how well is the distribution of knowledge in these models. And we always assume that each and every part of the model would be so important, but turns out it's not so. And everything is not so localized that we thought that. So the information is stored and spread across the entire model.
Is that actually true? So what they're doing in the layer pruning procedure is they're finding the block with the minimum distance between the inputs and the outputs, right?
Sorry, what?
So the pruning procedure is not random, right? So they're
Yes.
they're finding the span that has a minimum angular distance between inputs and outputs. So
Yeah.
basically what it means is that you can skip that part of the activations and just activate the bottom parts. So
The
that means
bottom.
that the information would be more localized rather than less localized.
What I meant by that was that we assume, let's say, if we remove those three layers, and we assume like that every part in even in those three layers, something very important for those, for the final tasks would be present in those three layers that we removed. But that is not true. So when I meant localized, what you're saying is true. But what I meant to say was that not each and every part of the model is as important for all the inputs that we think of.
Yeah, I think what a lot of what it's saying is that there's significant parts of the model that are just not being used for the computation or that you can cut out. And so you can do this layer-wise pruning. You can also do like node-wise pruning, etc. And yeah, to your point, like the model capacity is really not being maximally used, at least if we consider this data set. Maybe that's important for other data sets, but for this data set that they're looking at there, it's not well used there.
Yeah,
Oh,
absolutely.
that's actually a really good point. Is this like, is it that the other layers are, yeah, like encoding information for like different types of tasks? Like, I wonder if they like limited this too much by just doing question answering.
They discussed the QA benchmark and the validation loss on C4, and the pretty much the same results on both of them. And as I said earlier, that
C4,
uh,
C4,
that
what's C4?
can be a function of the task itself also. Like maybe different number of layers are removed in for different tasks, but it
Uh-huh.
could depend on the task itself also.
That's fair. The other thing I was curious about is like, did it share any information on all these like sequential layers? Are they like actually just random layers? Like, are they dropping to 10, 12, 15? Or is this like a large chunk of sequential layers that didn't add any value?
Yeah, so that
Oh, that's a good.
will answer your question.
Mhm.
So basically, this color here shows, I'm not sure, is this yellow? Yeah, this yellowish color shows the angular similarity of angular distance between layers. And you can see that across different models like Llama and Quen. For Quen, it is a bit different, but let's say Llama and Mistral, they have the same kind of pattern of this yellow angular similarity between these layers. And the most common thing that is present in all of these models is that the deeper layers have a lot of same angular distance. So which just shows that the deeper layers are not really adding that much to the task, and that is why the model is still able to perform well even after removing these layers. So
Yeah, what they're removing is the full span. So from L to this L plus N, that
yeah,
whole block.
yeah. So for example, here in this Llama 27B, they would remove from layer 20 to 30. And still sort of get similar performance because the angular distance between layer 20 and 30, not exactly like, but layer 22 to let's say 29 is quite similar. So the performance does
And
not
this is
decrease.
the angular distance between the weights, right?
Between the after each layer output. So basically after layer number 10, the output that we get and the like for each layer. So after layer 20, the output that we get and the between the layer,
By output, do you mean there's some fixed input that they're putting in, or
no, like it's a transformer block, right? So the input
yeah?
goes to the transformer block and whatever output that comes out of it, that thing.
But in order to have an output, do you, okay, I don't know.
So in order to have it an output, it will have to go through the self attention and the MLP block of that particular layer. So whatever output that we get after passing through these two components,
But
that
passing what?
sorry,
Passing what? Are you
passing
taking like data
input.
samples from the data set?
Yeah. So let's say we have a transformer architecture, right? And we have 10 layers into it. So the input to each layer is the original, is the out, is the, wait, how do I explain this? So each transformer block gets the same input, not the same input. So let's just take a 3-layer transformer block. Okay. So for the first layer, the input is the embeddings of the original text input. Okay. And then we have a skip connection for this embeddings to the next layer. And this embedding input is then passed through the block one, the layer one of the transformer. And in that layer, it will go through a self-attention block and then the MLP block. That would give us some output. So this is the output for the layer number one. And this output is added to the skip connection output that we have. Did you understand that?
Yeah, of course.
Yeah. So this is basic the output here is the output of the layer number L. And so the authors show that the cross models, the deeper layers tend to be very similar, though the deepest blocks that include the final layer are nearly maximally dissimilar. So if you see all the last blocks that are there, they are quite important for the functioning of the model, and they are not similar to rest of the layers. Um, okay. And they also tried, a simpler pruning strategy. Like here, they were trying to find the angular distance between layers to find the similar layers, but they tried with simpler strategies of removing the, let's say, last n layers, or the last n layers directly, without with keeping the last layer intact. So if pruning n layers from an L layer model, they would remove layers L minus into L minus 1 so as to remove the deepest blocks that exclude the final layer. So you can see here the comparison between the similarity method and the simple baseline, like basically removing the last layers. So evaluation of Llama 2 70 billion model. And here you can see that if you just randomly remove the last layers, the performance degrades quite quickly, even without healing. But if you use the similarity method, you can have, like um, for Llama 270B, you can remove up to 30% of the layers and still have good enough performance. So just randomly removing these layers did not work well, and the performance here is on three different. We have already seen on MMLU accuracy and the C4 validation loss. We can see here for the bool QA dataset accuracy also. And interesting thing is that if we remove, with these, if we just randomly remove the last layers, okay, last, let's say 5 or 10 layers, but we do it with healing, we see that the performance still continues well. So, um, so especially for Llama 270B model, you can just randomly remove, let's say, 30% of the last layers and do this sort of a fine tuning, and you can still get the original performance that was there with that could have been there if you would have used the similarity method to select the most optimal layers to remove. So this basically shows that the similarity as a metric is necessary if you don't want to do any healing post the pruning of layers. But if you are anyways planning on healing, doing some sort of a healing, then you can just use a simple heuristic of removing, let's say, the last 30% layers. And yeah, that's it from my side. Any questions?